All right, let's get started. So, what were we talking about in chapter 5? Last week? Measuring segments. So, we remember this notation now. So, if I have some segment AB, I put a bar above the segment to represent the length of the segment,
right.
AB. And remember that length is always in terms of some unit.
Right.
And so, if I'm going to say this is equal to 5 what? I already have to have some predetermined unit established. So if my unit is this segment over here, CD, then maybe AB has length 5, which means AB is exactly 5 of these things.
Right.
Right?
Yeah.
Okay. So we talked about the length of these segments. We introduced 2 postulates last time. What were our 2 postulates last time?
There's postulate.
Our 2 axioms. Is this axiom group
I
4?
have a question. No, it's 3.
You sure?
Also. Oh, well, that's where you're at.
Axiom group 4. We had 2 new axioms.
I have a question.
Go ahead.
If you are trying to prove with an image that a line segment is shorter than a different line segment, you have to make a point on that line segment
It's actually like the 50.
to that would make the shorter line segment even to the one or congruent to the line segment.
So when I say that the segment AB is less than CD, what precisely does that mean? That means that there exists some point B prime in CD, or we'll just say there exists B prime such that AB is congruent to CB prime, and we have CB prime D, and B prime is between CB. Pictorially, it looks like this. Here's the picture for AB is less than CD.
Okay. Yeah. That's
Very different from the picture CD is greater than AB. Those have different pictures, different definitions. What's the picture for this one? This would be that there exists D prime such that CD is congruent to AD prime, and we have AB D prime. So for that picture, instead of our prime point being here, it would be you need to extend this one on a line. You mark D prime here, and here would be the picture for CD is greater than.
Right.
Now it turns out those are logically equivalent, and we proved that. But those are each of their individual definitions. And they're very different definitions that turn out to give the same thing. Any other questions on that? So that was lesson. And so, with our axiom group 4, last time we had 2 new axioms introduced. Remember what they were?
Yeah, true.
We had first off the Archimedean one. Does he call them axioms or postulates? Sorry. Yeah. Sorry, he called them postulate groups. So we have the Archimedes postulate. What was the Archimedes postulate?
Where you can determine whether a certain the line segment was longer or shorter.
It was our postulate that told us basically we can measure line segments and we can measure them as long as we want. Remember, prior to this postulate group, if I had some point A on a line, I was never guaranteed that I could get some point beyond some distance. We were never guaranteed that before. I was always guaranteed I could find a point beyond this point, but maybe, let's say maybe my point beyond this point is only half the distance between here and here. So imagine this. I'm guaranteed there's a point beyond this point, so maybe it's the one that's half this distance, so that gets me to here. I'm guaranteed there's a point beyond this point, so like maybe that's one that's half this distance, so it gets me here. And then here, and then here, and then here. I'll approach this distance, but that's never going to get me this far. How do I know I have points clear over here? What guarantees me I have points clear over here?
We're missing this chair in there.
Yeah, I was missing one in here too. He can take this one, I'm not going to sit. And so, we were never guaranteed that we get a point beyond this point. We were never guaranteed we could get a point a certain length away. So what the Archimedean axiom said is, it's kind of a convoluted one, but it's the one that lets us know we can get as far as we want. So say I've got this segment AB, and I've got my unit here, CD. The Archimedean property says that there exists some n in the natural numbers. There exists some number of intervals we can use. It basically says you can count off some number of these intervals and eventually get to or past that point.
There exists a number in natural numbers.
Yeah, there exists some little n in the natural numbers. Some number 1, 2, 3, 4, 5. Some number in there. Such that if you were to count off that many segments here, you could eventually get to B or get past B. There's some number of segments I could measure this with, so I'd eventually get to or past B. Right?
Right.
That's what it says. So it says there exists n in n such that, let me get my verbiage here right so I don't say anything wrong. There exists n in n and a sequence of points of points A1, comma, A2, comma, dot, 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 comma, AN, such that, so the sequence of points are going to be our sequence of points that we list up here, giving us our segments. So here's A1, here's A2, here's A3, dot, 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 coming all the way down. Here's A sub n minus 1, our second to last point, and then here's our last point, A sub n. So there exists some sequence of points I can find on this line, such that each of these segments are congruent to CD. So that is congruent to that, is congruent to that, is congruent to that, is congruent to that, dot, 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 is congruent to this last segment. It's congruent to this. So such that CD is congruent to A to A1, is congruent to A1 to A2, oops. A1 to A2 is congruent to dot, 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 is ultimately congruent to A sub n minus 1 to A sub n. And either A sub n is equal to B, or we have B between A sub n minus 1 and A sub n. So you can measure out this segment, and you'll either eventually land exactly on B, or you'll get a little bit past B, in which case B will be between the points of your last segment. It will lie on your last segment.
Right.
Right?
Yeah.
And this was essentially gives us also our process for measuring. When you measure how long something is, so you start out with our meter stick here. If I was measuring the points between 2 points, you know, I measure this A to B. Well, shoot, that already got me a full meter. Let's pretend I was measuring just the length of this whole whiteboard. So when I'm measuring the length of this whole whiteboard, what do? You know, I count my line up a meter. I say, okay, that gave me 1. That gave me 2. 3 gets me too far. So my Archimedean principle was telling me that there was some natural number, in this case 3, such that if I count it off, I'll eventually get exactly where I was trying to go, or a little bit too far.
Right.
Right?
Yeah, right.
And then, for our process of measurement, we make this recursive. What do? We say, okay, so I got me 3. Was it 3 or was it 2?
It was 3.
2 got me too far. So 3
All right.
3 got me too far, so 2 is what it is. And then what do? As a general rule, we then decide, okay, rather than using meters now, is this a yardstick?
Yardstick, right?
We'll pretend this was a meter stick. Rather than doing meters now, I'm going to do,
Centimeters.
not centimeters, we're not going to skip all the way to hundreds of meters, but decimeters. We're going to do 1/10 of our previous measurement. So every 10 centimeters now. And so then I would come and measure this, and I say, okay, here's 10 centimeters, 10, here's 10, well, here's a decimeter, here's a decimeter, and 3 decimeters gets me a little too far. And so it was 2.2 meters, 2 decimeters, and now I come measure with centimeters, and I say, oh, let's see, 5 centimeters gets me too far, so we put a 4 here. And I keep measuring, maybe it goes on forever. I measure this thing, maybe it's an irrational number, or maybe it comes out to exactly 695. And so what the Archimedean postulate gives us intuitively is that if we have some segment, if I start out with some segment AB, then I know that there exists some real number, some x in R, such that the length of AB is equal to x. I can find its length, and its length is going to be a real number. That's what the Archimedean postulate intuitively gives us. If you have a segment, you can now determine its length. You can find the real number that represents the length of that segment. A real number, decimal number, same thing. Hopefully that's not confusing you.
Right.
Then we had our second axiom, or our second postulate, which is the completeness postulate. And what does the completeness postulate give us? The completeness postulate gives us the reverse thinking here. The reverse postulate says that if I have some x in the real numbers, then that means there exists a segment AB such that the length of AB is equal to x. So the completeness postulate is the one that told us that pick any real number you want, I can find a segment of that length. Pick any length you want,
Right.
I can find a segment of that length.
Yeah.
The Archimedean property says, pick any segment you want,
We find length as.
we can find the length. The completeness one says, pick any length you want, we can find the segment. And that's how they're counterparts to each other. Make sense?
Yes.
Okay. So those were the big postulates for section 5. And then I don't think we proved any of the theorems yet. Chapter 5 is kind of a weird one. You're going to notice that if you read through the proofs of these, they're going to be a bit unsatisfying. It's because really, some of the concepts we're touching on upon here are really concepts that you come across in the calculus class, a real analysis course. And the author, we can't do a deep dive into doing all this stuff complete. Like, we say, you get the process for measurement, right? And we kind of have to leave it at that. That's not very rigorous, that's not very precise, but it's kind of what we have to leave it at as a limitation of the course. And so the author is trying to do 2 things at once. One, he's not trying to say, now all that algebra stuff that you should already know, we're going to throw that at you out of the blue and just start using it without ever mentioning it in the class. On the other hand, he can't completely rigorously cover this material. It's why chapter 5 is such a weird one. It's why we can't give you a lot of proofs in it. So even the proofs that he does and that we're going to do, you're going to notice that they're a bit unsatisfying and they feel a bit, it's going to keep feeling a little bit like you're cheating. It's because a little bit we are cheating. It's because we can't do this section completely rigorous. Because measurement and getting at ultimately what we're working our way up towards is things like areas. Area, you can't give it a precise definition in just a geometry course. The definition of an area is an integral. And that's how you have to define it. And so we're trying to come at this idea in a backdoor sort of way.
You can't define it or you can't find it.
You can't define it. The definition of area is an integral.
Integral.
An integral. An integral from calculus. An integral.
Never heard that.
You've never heard of an integral? Oh my goodness.
Never took calculus.
Yeah, but I can't believe you've never heard of a derivative either?
Derivative.
Ah. derivative and integrals go hand in hand. An integral is an antiderivative in a way. It's the reverse process. It is to derivative what division is to multiplication, what subtraction is to addition. In a sense. Okay. But integrals are what we use to calculate areas. That's what you do in calculus. If you have calculus and you're given some curve like this, your job is to find, if we're trying to find the area of the curve from here to here, this is the curve f of x. We're trying to find its area from the point A to the point B. That's exactly what the integral from A to B of f of x with respect to x is. That gives you the area. In English. So that's what an integral is. But, so we have to come up with stuff in kind of a fast and loose way. All right, so let's do our first theorem now. And you'll see a bit what I mean and why we won't really have you doing proofs like this. Okay, so starting with theorem 5-1. Theorem 5-1 says, if AB is congruent to A prime B prime, then the length of AB is equal to the length of A prime B prime. Now hopefully that's already intuitive, because when we were trying to motivate this idea of what does it mean for two segments to be congruent, we said it means for them to be the same long. That was the intuition we were using when we were talking about two segments being congruent. Now we're going to prove that that is in fact what it means for two segments to be congruent. If two segments are congruent, then they in fact have the same length. Okay, so let's get started. First, let AB and A prime B prime be segments such that AB is congruent to A prime B prime. And let me draw a picture over here. So here's A, here's B, here's A prime, here's B prime. Okay. So 2. From the Archimedean property, we know that there's these points. So let C1, comma, C2, comma, C3, comma, dot, 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 be the sequence of points between A and B, determining its length. Okay.
So you're saying from C1 to C2?
So remember that when we do this measurement process, we create a sequence of points, right?
Right.
Until I get to here.
Which are units.
And then units. And then we switch to tenths now.
Right.
And we start creating a sequence of points. And then hundreds, and thousands, and 10,000s, and 100,000s. Potentially doing this indefinitely, creating an infinite number of points, or potentially terminating at B. So C1, C2, C3, this is potentially infinite number of points. Maybe it's finite, maybe it's infinite. But it's all the points we do in the measuring process when we approach B. So maybe C1 would be here, C2 would be here, C3 would be here, C4 would be here. That lined up too closely. Pretend C4 only went to there. And now we need to change our unit lengths. And so now we'll have C5 here, C6 here, C7 here, C8 here. And then we need to change our unit lengths.
C10, C12.
Right. Maybe there's infinite, maybe it terminates. And there's the hand waving that we're doing, that we're not being very precise how exactly that measurement process goes. We kind of gave you a feel for how it goes. I say, it works, right? And you say, appeals to my intuition. And we say, okay, good. And we go on. But that's where the hand waving is. That's where we're kind of cheating, which is why it's somewhat unsatisfying. Alright. Now, let C1 prime, comma, C2 prime, comma, C3 prime, comma, dot, 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 be a sequence of points on A prime, B prime, such that A prime, C1 prime is congruent to AC1, comma, C1 prime to C2 prime is congruent to C1, C2, comma. So we're coming and we're marking points over here. Here's C1 prime. And by definition, this is now congruent to that. And I'm going to mark C2 prime now over here. And by definition, this is congruent to that. And I'm going to mark C3 prime over here. And by definition, or by choice of what these points are, that is congruent to that. So this segment is congruent to that segment, and then pick the next point, C3 over here, so that C2 prime to C3 prime is congruent to C2 to C3, comma, dot, dot, dot. So all these congruences hold.
Till you find what point lands on B or B prime. Isn't it?
So we're just marking off now. So I have this sequence of points up here which measures this. And now I'm just going to create a point. I'm going to pick the point on here such that this is congruent to that. And then I pick the next point on here such that this is congruent to that. So I keep building it up so that my sequence is always congruent to the above sequence.
Right?
Maybe the sequence goes past B prime, maybe it stays way over here and never approaches B prime. We know it's going to in fact end up getting exactly to B prime the same way that this one gets to B.
Right.
But that's the point of the proof. Now, I use theorem 3-4 to prove this. So let's really quick recap exactly what 3-4 says. I should have done that before I started this problem. Didn't read that. Probably easier to find my notebook than the book. Okay. Not 3-4, 4-3. Okay, theorem 4-3, remind us of it over here. I can get intuition for it really quick. So theorem 4-3 was that if AC is congruent to A prime, C prime, and we have B prime between A prime and C prime, and B is a point on C's side of A, comma, then, B side of A such that it's congruent to. B is a point on C side of A such that AB is congruent to A prime, B prime. Then B is between A and C. So let's draw a picture for this. Something we already proved. Remind us of this proof. So I've got my segment here. Here's my A. Here's my C. Here's my A prime. Here's my C prime. So if AC is congruent to A prime, C prime, so this is congruent to this, and B prime is a point between A prime and C prime, so pick some point over here, B prime, and B is a point on C side of A. So here's A, B is on the same side of A as C, such that AB is congruent to A prime, B prime. So B's right there, so I said this is congruent to this. So I know that segment's congruent to that segment, and I know this segment's congruent to this segment.
Thus we know that BC is equal to B prime C prime.
So we would know that this segment is congruent to this segment, that's true.
Right.
We knew that from before. But what's more important is we know also that B has to lie between A and C.
Right.
So I know that those segments are congruent, but maybe B was somehow after C, and C is the point that came first.
So that's can't work.
Well, yeah, right, we proved it can't work. Obviously, from the picture it can't work, we did a proof last time, maybe not last time, maybe the time before, that it does in fact have to be between. And we did that proof by contradiction, assume it wasn't, and we showed that you could get something less than and congruent to itself, I think is the contradiction we got. Okay, so that's the theorem we are using now. Over here. So let's see. So I know that C1 is between A and B, right?
Yeah.
And I know that AB is congruent to A prime B prime, and A prime to C1 is congruent to A to C1. So I know that C1 prime has to be between A prime and B prime.
Right.
And similar thinking for C2 prime,
And C3.
and C3, and C4, and C5. And so 4, I could probably just say it like this now. By theorem 4.3, comma, all points, or maybe better to say the sequence, C1 prime, comma, C2 prime, comma, C3 prime, comma, dot, 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 lies between A prime and B prime. Okay, so I've got this sequence of segments that completely lies between A prime and B prime,
Right.
Yeah.
where all the lengths are exactly congruent to the lengths up here. And so this sequence measures off A prime, B prime.
Right.
Again, not very satisfying, but since we talked about measuring in such a high level way, that's our notion of measuring. Come up with the sequence of points between them, this infinite sequence of points between them, and we count off the lengths as, we count the segments as measuring. And so we measured this segment the exact same way we measured this segment, therefore they have the same length.
Yeah, but they're not. How does that prove they're equal? We know they're congruent. They have the same length, but they're not. How does it prove that they're equal? Equal means they
Their
have the
lengths
same
are
length.
equal.
Oh.
That's what we were proving.
So
We were
isn't
proving
that
if they're
the definition
congruent.
of congruency?
No, no, no. What's the definition of congruent?
They have the same length.
Same property.
They're the same.
Yeah. Same.
What is the definition of congruent? Bad question.
It's an undefined term.
It's one of our undefined terms.
So we don't have, okay, so thus it's not.
Therefore, these six have the same thing. Yeah, let's briefly talk about that again. It's worth reiterating that because that's big picture what geometry is. So that ends that theorem. Not very good, but there it is. Okay, back to what we're talking about. In general, we're talking about axiomatic systems. Geometry is just an example of an axiomatic system. The point of studying geometry is to get you competent in axiomatic systems.
Right.
That's the big point. Every axiomatic system is composed of 4 things.
Undefined terms.
Undefined terms.
Defined terms, right?
Undefined terms. So far, what are our undefined terms in this class?
Line, no.
Point, line, and plane.
Plane,
Oh, yeah.
between,
Point,
Between-
line, plane,
Yes.
between,
congruence.
congruent.
I think that's it.
Is that
I
it?
think so. I think we're on.
What about less than?
We haven't said.
No, less than has a definition. That's the first thing we went over today, is the exact definition of less than.
Oh, yeah.
And less than is defined in terms of
Congruence.
congruence and betweenness. So we use these things to define what it means to be less than.
Right.
So you're saying we use those to define things, but they can't be defined?
Yes, these things do not have definitions. Does that mean that they don't mean anything?
No.
How is a word given meaning if it doesn't have a definition?
Because you don't know exactly what it means. You can't prove
You
exactly
can't
what it
prove
means.
it. You can't prove what it is. Right?
Does this word mean anything? How do you know the meaning of a word? You go look it up in a dictionary. You look at its definition. Okay, I just told you that this word doesn't have a definition. So is it a meaningless word?
No.
How does it
Yes.
have any meaning?
Technically, yes, it is. But at the same time, no.
What's the second part of an axiomatic system? We have undefined terms,
Theorems.
and then we have axioms or postulates. Typically we say axioms, in geometry we say postulates. What are our axioms? These are our basic assumptions, right?
Our axioms are
Same thing as postulates, basic assumptions.
terms, theorems, definitions, axioms, postulates.
The axioms are our basic assumptions. Every line has at least 2 points. We didn't prove it. There is no proof for it. That was a postulate. That was one of our axioms. Right?
Right.
Now notice what that axiom just said. It said every line has at least 2 points. It was relating these terms together. So while these terms don't have definitions, that does not mean they're meaningless. They're given meaning through the axioms.
Right, so the axioms.
So what are a point? I don't know exactly what it is, but there's 2 of them on a line. I know that. What's a line? I don't know exactly what it is, but it's got 2 points on it. I know that. So they're not meaningless. The axioms are what give our undefined terms meanings. Our axioms relate our undefined terms to each other.
Right.
And then we have, from here, we have the basic ones. We have what you do throughout the rest of class. We have definitions. Definitions, we either use undefined terms to create definitions, or we use terms that we've already defined. So when I define less than, how did I define less than? I defined it in terms of betweenness and congruence.
Right.
When I define less than or equals, I define that in terms of less than, something we already had defined, and congruent.
Wouldn't a line be defined by
Lines defined
it's
by 2
undefined.
points, which means it's still undefined at 2 points.
like I know what it means, but like it's hard to explain.
And then finally, we have our theorems.
A segment is not an undefined term.
No, a segment is not an undefined term. We use points and lines to define a segment. Or, also betweenness. Because what is the segment AB?
It's between.
So here's
It's the
A,
line. It's the
here's
line
B.
between A, B.
Right, it's all the collinear points that lie between A and B.
Which there's an infinite amount.
Huh?
To which there's an infinite amount.
Which there's an infinite amount. The point is, you define a segment using points in between us. So, undefined terms, axioms, then your definitions, and then your theorems. What are your theorems? High level language, what's a theorem?
Proving something. It's
You prove it. What does it mean to prove something?
Means you can use your axioms to define it.
Not define it, but you show it's implied by your axioms.
yes.
You show that if the axioms are true, then all the theorems must be true. All the theorems are if-then statements. We started all the way back with the axioms, and we started putting axioms together to prove theorems.
Right.
And now, well, we expand our axioms as we go to prove new things, but we also go back to theorems to prove new theorems.
Right.
But since this theorem was proved just by the axioms, then we're still just using the axioms ultimately.
Right.
Ultimately, in proving a theorem, I never have to use a previous theorem.
You can just prove it.
I can go all the way back to the axioms and prove it from scratch. I never have to use a previous theorem. Similarly with the definitions, I never have to use a definition. I can always go all the way back to all my undefined terms. I didn't need to use less than to define less than or equals. I could have gone back and just used betweenness and congruence.
Right.
Make sense?
Yeah.
So let's big picture what these systems are, these axiomatic systems. Don't know why I wrote that. We don't have enough space for the next theorem there. I don't think we'll really need to make reference to these. Let me check the next one really quick to see if we. I think I just didn't even like the author's way of doing it and just did it. Alright, let's go to the next one. So we'll only prove one more theorem in this section. I'll give you the next two. I don't think that there's a lot of value in going through them as much, these types of proofs, because there's no way that you'd come up with that way of thinking about it on your own. There's no reason that you should. It's hand wavy. So our next theorem. First, I'll just write them all out. That'll be better. Theorem 5.2. This one says it's the converse. If if the length of AB is equal to the length of A prime B prime, then that gives me that AB is congruent to A prime B prime. Theorem 5.3 gives us that AB is greater than A prime B prime if and only if.
Wait, you're saying you're not gonna prove?
I'll prove this one and then we'll leave it at that.
Well, the 5.2 is kind of obvious to me. They're equal, then they're the same points. They're the same points.
No. This is not saying that they're equal. That's saying that their lengths are equal. Never am I saying segment AB is equal to A prime B prime. We will hardly ever say something like this. This is saying that they are identical segments. When I put the line above it, that's a number. That's the length of AB.
So it's saying 5.
And that's a number. And so that is saying 6 is equal to 6, or something like that.
Right.
It's definitely not saying those segments are equal to each other. That's a good point to bring up. So, this is not saying if two segments are equal, then they're congruent. We already proved that earlier in the class. This is saying if the lengths of two segments are equal, then they're congruent. Theorem 5.7 says if AB is greater than A prime B prime, then the length of AB is greater than the length of A prime B prime, and vice versa. If the length of AB is greater than the length of A prime B prime, then AB is greater than A prime B prime. And then our last theorem, which this one the author doesn't even bother proving, because a lot of work for a small payoff in terms of geometry.
Yeah.
But this one says, if the length of AB is equal to x, when CD is the unit, when CD is the unit, comma, and the length of CD is equal to y when EF is the unit, comma, then the length of AB is equal to x times y when EF is the unit. Okay, this is very intuitive. Let's get a picture for that and then we'll come back to our proof. These markers are kind of dying on me. Okay, so here is AB. Here is CD, so here's A, B, CD. I'm trying to draw it so that AB is 3 CDs. So right now I want the length of AB to equal 3 when CD is the unit. So maybe I'll put our unit right here. We'll create a little table here. So AB equals 3 when CD is the unit. However, here's EF. And let's say that the length of CD,
3.
I don't know, how many of those does it look like? Maybe 5?
4.
We'll just say 5. The length of CD is equal to 5 when EF is the unit. Question. What is the length of AB when EF is the unit? If I would have measured AB with EFs,
15.
how many would it have been? 15. Because it takes us 5 to get one of these and 3 of these to get one of those. So 5 times 3.
Right.
That's all that theorem is saying.
5 groups of 3. Or, yeah, no, 3 groups of 5.
3 groups of 5. So now read this and I think it'll make perfect sense. If the length of AB is x when CD is the unit, so that's AB equal to 3. Here's our x. So up in our proof, this is giving us our x, this is giving us our y, this is giving us our x times y.
Wouldn't it be EF?
So the length of AB is x when CD is the unit. So the length of AB is 3 when CD is the unit. And the length of CD is y when EF is the unit. The length of CD is y when EF is the unit. Then the length of AB is x times y when EF is the unit. Perfectly intuitive?
Yes.
Okay, so that's that one. And that's the end of that chapter. So I'm going to prove this one and then won't bother with the rest of these. The proof of this, the author has it. It's very similar thinking to the proof that we did for this, and then he doesn't even bother with that one because too much work for the payoff. So now we'll just do theorem 5.2. 1. So let A, B, and A prime, B prime be segments such that the length of AB is equal to the length of A prime, B prime. I'll do my picture over here. I didn't really draw a picture with this, but I want to walk you through my thinking. So I'm going to have A, B here, and A prime, B prime down here. Now, what am I trying to show? I'm trying to show that AB is congruent to A prime, B prime. Right? So, let's see, let B double prime. Okay, so here's what I'm going to say. I'm going to say let B double prime be the point down here such that, so maybe right here, let B double prime be the point down here such that A prime B double prime is congruent to this. So I know this and this have the same length, but I don't necessarily know they're congruent. It turns out they are congruent, but we don't know that yet, right?
How can they not be congruent if they have the same length?
They can't. If they have the same length, then they're congruent. That's what we're proving. So we're drawing a possible picture.
Right. We know this
This
picture.
picture's locked.
This is logically.
Right, so we're going to do a proof by contradiction. So I'm going to set up an impossible picture. It's like the same way that I draw a picture where a line goes like this. How can a line do that? It can't. And so that's how we know that we get something bad. So, impossible picture. But so far, all I know is that the length of AB is equal to the length of A prime, B prime. That's all I know. I don't know that AB is congruent to A prime, B prime yet. That's what I'm trying to prove. So I say let B double prime be the point on here such that AB, may as well just write over here, 2. Let B double prime be on B prime's side of A prime such that AB is congruent to A prime B double prime. So pick the point over here, and that makes it congruent. So now this segment I know is congruent to that segment. And I know that B double prime, it turns out, is going to be the exact same point as B prime. So assume by way of contradiction that they aren't the same point. So 3. Assume by way of contradiction that B prime is not equal to B double prime. Okay, if they're not the same point, then we have two possible pictures here. Either B double prime was on this side or B double prime is over here. And I don't know which. So B double prime could be here or B double prime could be here.
Right.
I'm going to show both are impossible, therefore it has to be there. It can't be on that side of B prime, and it can't be on that side of B prime, so it has to be B prime.
Right, because.
Okay.
Or A, B, and A, B.
Assume by way of contradiction that B prime is not equal to B double prime. And so either we have A prime, B, and let's see which case do I handle first here. It doesn't matter. A prime, B double prime, or A prime, B double prime, B prime. So we have to have one of those two cases.
Okay, yeah.
Okay. Now, just a note from our previous theorem. Observe that AB congruent to A prime B prime implies AB's length is equal to A prime B prime's length. This we just know from our previous theorem. So if I get those two segments, oops. B double prime, sorry. There we go. I know that since AB is congruent to A prime B double prime, then they have the same length. That's from our previous theorem. So wherever this B double prime lies, I know A prime to B double prime has to have the same length as A to B. Yes. So I know, here's what I'm trying to prove, here's what I know. I know AB's length is equal to the length of A prime to B double prime, because those are congruent. That's using our previous theorem.
Yes.
Okay. So now let's handle each of the cases. 5. If we were to have A prime, B double prime, our first case, then what do we get? We get that the length of A prime, B double prime. So if B double prime's length is, if we know B double prime is for sure on that side, then its length is going to be the length of this plus the length of this.
Yes. Okay.
So it's going to be the length of A prime, B prime, plus the length of, remember these are now numbers,
B prime to B double prime.
B prime to B double prime.
But that can't be because we know that A prime B double prime is congruent to or equals
Yeah,
AB.
We're
AB is
right on
congruent
the
to
door
A
there.
prime B prime.
So I know that this has some length, A. I know that this is a non-zero value since they're not the same points.
Right.
So in other words, this is equal to A prime B double prime is equal to the length of A prime B prime plus some number A. I don't know what it is, but it's going to be some number A. Right?
Yes.
Okay. Now, how does this length compare to this length?
Very good.
Oops,
Wait.
I put an equal sign there. This was supposed to be an arrow. Okay. So how does this length compare to this length? Oh, I wrote the same thing twice.
So it's
Oh, no, okay. All right, we're good. What did I do here? A prime B double prime is equal to the length of A prime B prime plus B prime B double prime.
Right.
That gives me that A prime B double prime is equal to the length of AB. Why did I do AB rather than A prime B prime?
You did do A prime, you did.
I did AB on my paper.
Oh.
Which means I had an obvious piece of thinking that now I'm not seeing.
Oh, because
Because right here, our given information.
Right.
Okay. So using our given information, which is why it was so obvious, I didn't bother shading it. One of the problems with reading a proof off the paper rather than just thinking it out yourself. Okay, so since those are equal, then this can be rewritten as, I could have replaced the A prime B prime with just AB. You with me?
Yes.
So I did substitution two things. B prime to B double prime, that's just some number A. And then the length of A prime B prime is equal to the length of AB. That was given information. Okay, so now right here, notice that the length of AB is equal to the length of A prime B double prime.
Yes.
So I know that this number is the same as this number.
Right.
So that gives me that, subtract that value from both sides, I'm left with 0 is equal to A. Contradiction. I'm saying A has no value.
Right. Yeah.
Similar thing if we go this way. So 6, look at my paper, let's just think about it. If we would have had A prime, B double prime, B prime, then that would give me that the length of A prime, B prime is equal to the length of A prime, B double prime plus the length of B prime, or B double prime to B prime. So if we would have had it, now we have it, this picture, the point's here. So the length of this is equal to the length of this plus the length of this.
Right.
Again, I know that the length of A prime B prime is equal to the length of AB. So I'm going to rewrite this as
and if it's
AB's length.
and if the length of AB is congruent to A prime double is equal to A prime B double prime, that means A prime and B prime are equal to A prime B double prime, and that's impossible.
Basically, because you're going to, for this other value to be 0.
Okay.
So I replaced the length of A prime B prime with the length of AB. That's all I did going from here to here, and just calling this some positive number A. I don't know what it is. Well, what does that give me? Again, since the length of AB and the length of A prime B double prime are the same, subtract from both sides, we get 0 is equal to A. Contradiction. 7. Therefore, B prime has to equal B double prime. They have to be the same point. Make sense?
Yes. Wouldn't that be contradiction?
We have the contradiction in this case and the contradiction in this case. Therefore, neither case can be true. And so, if it's not the case that B prime is between,
That's not
if it's not the case that B double prime is on that side of B prime, and it's not on that side of B prime, it has to be right on B prime.
which thus shows because AB is equal to A prime B prime.
Yeah, we
That
should finish
shows
this
that
out.
sense.
Good point. We should finish this out. So that gives me that AB is congruent to A prime, B prime, which is what we're after. Okay? All right, that is it for chapter 5. Yeah. Not sure. Should we start chapter 6? Maybe we'll kill it there. Okay, so that will be the end of chapter 5. We'll get homework done and then test. Start chapter 6 next week. Oh, I didn't send your test.